Okay guys, so I figured I would record myself doing two of the even numbered questions on page 761 to help you with the odd number ones that you were assigned. So we'll start with question 42 and then we'll do question 44. The other ones that you have to do are very similar to this, so the procedure should be the same. So if you look at question number 42 in the book, it basically says that you have a 30 milliliter sample of 0.150 molar potassium hydroxide and you titrate it with 0.125 molar perchloric acid solution. Calculate the pH after the following volumes of acid have been added: 30 milliliters, 35 milliliters, 36 milliliters, 37 milliliters, and 40 milliliters. These are really easy questions to answer, but they're very time consuming because each of these parts is going to require you doing a rice chart. So first things first, we should start with our reaction. Alright, so you'll notice here in my reaction I split my potassium hydroxide apart. And the reason why I did that is because it's a strong base. The perchloric acid is also a strong acid, so I split that apart. When you perform the double replacement reaction, you end up making potassium perchlorate, and that happens to dissolve in water very well, so you leave it in ionic form on the right-hand side. And then the hydrogen and the hydroxide come together to form water. So in the original question, they told me that I had 0.15 molar hydroxide, or potassium hydroxide, and that liberates 0.15 molar just hydroxide ion, and then 0.125 molar hydrogen ion. And the key here, though, is that you have to realize that the second that you mix the hydroxide with the hydrogen, you essentially dilute the hydrogen and you dilute the hydroxide. So these are not really your starting molarities. You're going to have to change the molarities to account for the volume, the additions, additive volumes that occur when you mix 30 mils of potassium hydroxide and with another 30 mils of hydrogen ion. So you're going to have to adjust these volumes, and you can use the CV equals CV formula, or I'm going to use a rearranged version of that in the context of this fence post. So if you look at the question itself, they told you that you used 30 milliliters of hydroxide, and then you added another 30 milliliters of hydrogen ion, so the total volume for that mixture is 60. So your initial concentration of hydroxide really isn't 0.150, it's really half that. And half that happens to be 0.075. So that's really your initial hydroxide concentration. In terms of your hydrogen ion, you would do the same thing. Your original molarity really isn't 0.125, it's really half that, or 0.0625. Alright? Now, you should realize that at this particular point, one of these two substances is a limiting reactant. And the limiting reactant is going to be hydrogen. So you're going to lose 0.0625 from both columns here on the left-hand side, and that's how much water you're going to gain. That's how many moles of water you're going to gain. Okay? If you subtract, you end up with 0 hydrogen. In terms of hydroxide, the difference is 0.075 minus 0.0625, or 0.0125. And you end up with some water over here. No one really cares about this value because that's not really what you need to calculate pH. So if you look at the end of this rice chart, what do you notice? You notice that you have an end value at the bottom of the hydroxide column. Alright, so that's fabulous and fantastic because now I can get pH. I just can't do it directly. Alright, so what I can do is get the pOH, and if you recall, the pOH is the negative log of the OH. So we do negative log of 0.0125 on our calculator. That gives us the pOH. That happens to be 1.90. And then to calculate the pH, then we just simply subtract from 14 to get our answer. Okay? Alright, so the key here is to do the rice charts and see, okay, well, do I have a value underneath the hydroxide left over after I subtract out my limiting reactant? Or do I have a value underneath the hydrogen ion once I subtract out the limiting reactant? Alright, so because if you get the hydroxide, you got to go to pOH and then subtract from 14 to get the pH. If you have a value underneath the hydrogen ion column, then you can just directly calculate the pH just by taking the negative log of that particular value. Alright, so I'll show you how to set up the rest of the rice charts, but I'm not going to go through the full calculation to calculate the pH or the pOH, because otherwise this video might take way too long. Alright, so let's take a look at the next one. Alright, so in the next one, again, we're going to use 30 milliliters of hydroxide, but now in part B they're asking me to add 35 milliliters of acid. So then the total volume is 65. So then our initial concentration now is 0.150 times 30 over 65. So I'm just making this adjustment for these additive volumes. All right, and so I would do the same thing over here. The hydrogen ion isn't really 0.125 molar. It's 0.125 times 35 over 65. So it happens to be 0.0673. All right, of these two, again, the hydrogen ion is limiting. So you're going to lose that entire amount. All those hydrogen ions are going to react with the abundant hydroxides that are floating around them. All right, you end up with no hydrogen ion, and then let's see what that difference is. It's a small amount. You end up with 0.0019 hydroxides. You would do the same thing that we did in part A. Since you have a number underneath the hydroxide column, right? You have an N value here underneath the hydroxide. All you would have to do is do the negative log of 0.0019 to get the pOH, and then once you have the pOH, you subtract that from 14 to get the pH. All right, let's take a look at C. In part C, and you should notice that basically 30 milliliters, if you add 30 milliliters of acid to 30 milliliters of base, you should end up with something fairly neutral if they were the same concentration, right? We were definitely not there because the concentration over here for the hydroxide is a little bit higher, so we were already starting kind of on the basic side. If we keep adding more and more hydrogen, what we're going to expect is that the pH is going to get lower and lower, all right? Because we should be consuming less and less of the hydroxide as we go along. So your calculation should follow that trend. Let's take a look at C. So in part C now they're asking me to add yet even more acid, so hopefully the answer for this one's going to be even more acidic. They're asking me to add 36 milliliters. How do I do that? Same thing. All right, so this is going to be 30 over 66. This is going to be 36 over 66 that you multiply by the original concentrations in order to adjust those concentrations for these mixtures that we're putting together. All right, so this first concentration over here for hydroxide is 0.0682, and then for the hydrogen ion, it is look at that, 0.0682. Neither one of these things is limiting because they are provided to you in equal proportions. All right, so the amount of hydroxide that you're left with is 0. The amount of hydrogen that you're left with is 0. So something that has no hydroxide and no hydrogen ion that is in abundance floating around is only going to have a pH of 7. It's going to be neutral. All right, let's take a look at D. So in D, they're going to give me 37 milliliters of acid to add. All right, so then the adjustment here is going to be 30 over 67. Over here, it'll be 37 over 67. So let's take a look at what these new concentrations are that we're playing with. And let's see, so this is 0.0672. And over here for the hydrogen ion, it is 0.0690. All right, so in this particular case, now our limiting reactant is flipping. It is no longer the hydrogen ion, now it's the hydroxide. So I'm going to lose 0.0672 from both columns. I'm going to be left with 0 hydroxides and 0.0018 of hydrogen ion. Okay, so this is fantastic because I can now directly calculate pH. I don't have to do it indirectly. So all I simply have to do for the pH is just do the negative log of the hydrogen ion concentration, or 0.0018. Or the negative log of it anyways. And that happens to be 2.74. All right, so as predicted, we should be getting more and more acidic if we keep adding more and more acid. So part A, you notice the pH that was calculated was like 12.1, part C it was 7, part D it was 2.74. So the more hydrogen ion that you put in, the more acidic you should become. All right, let's take a look at part E, and then we'll jump off to question number 44. All right, so in part E now they're adding 40 milliliters of acid. Okay, so let's take a look here. So it's 30 milliliters of base over a total volume of 70. Over here it's 40 milliliters of acid over a total volume of 70. So let's take a look here. This initial concentration here is 0.0643, and then the initial concentration of acid is 0.0714. All right, so the hydroxide's limiting, and what we're going to have is an overabundance of hydrogen ion. As a matter of fact, we're going to be left with 0.0071. That's great because, again, I have a number underneath the hydrogen ion column. All I simply have to do is do the negative log of that value to get the pH. All right? So strong acid, strong base titrations are actually pretty easy. They're straightforward because you're either going to use the pH or the pOH formulas to calculate things. You're never going to have a situation where you would have to use the Henderson-Hasselbalch equation. It's either the negative log of the hydroxide if you have a number underneath that column, or the negative log of the hydrogen ion if you have a number underneath that column. For question 44, it's a little bit different because for question 44, if you notice, they're giving me ammonia, and I'm titrating it with a strong acid. All right. So in this particular case, the ammonia, you leave it together, the strong acid breaks apart. This ammonia is going to take that hydrogen ion and turn into ammonium, and then chloride is going to be floating around on the outside. And so essentially that's spectator, so you ignore it. So the equation that you really should have written on your paper is NH3 plus H yields NH4. All right? And if you notice, on the other question, we had two strong base with a strong acid. These form water. This form is soluble salt. When you cross out the spectators, right, the only thing that you have left is hydroxide plus hydrogen yields water. So that's why that was the reaction that I put in every single particular case. All right, this is going to be a little different. All right, here we're going to have a weak base on one side, strong acid, and then a conjugate on the other. So we might have a situation here where we could get a number that is underneath the hydrogen ion column. If you get that, you're golden because all you have to do is do the negative log of that particular number, and that would give you the pH. Or you might have situations where you end up with numbers here or there, in which case the math gets a little bit more complex. All right? Okay, so first things first. You're going to have to adjust these initial concentrations for the volumes that they give you in this particular question. So in question 44, they say that you start with 30 milliliters of ammonia. I wrote down the wrong concentration of hydrochloric acid. Okay, well, we're going to have to fix this. Well, that's not it. Sorry about that. So this was actually 0.03. And the hydrogen ion concentration really was 0.025. Unfortunately, I was reading a different question. All right, so we're going to have to change all those concentrations real quick. All right. And for part A, they tell you that you're starting with 30 mils of ammonia. And to it, you're adding 0 mils of hydrogen ion. Oh, okay. So then the total volume is 30 here, and the total volume is 30 there. So that means that you're starting with no hydrogen ion and 0.03 molar ammonia. And no ammonium. Okay, alright. This is ugly. Alright, if you look, what you have here initially, the only thing in the beaker that's present is a weak base. So we know it's weak because we memorized that. And so if you wanted to figure out the pH of this, then you would actually have to know the Kb of this, because it's a base, right? The Kb of ammonia actually happens to be 1.8 times 10 to the negative fifth. And to figure out, basically what we want is the number right here underneath this column, underneath the hydrogen ion column, because that's what's going to give us pH. For me to be able to get that number, I'm going to have to do these ugly Rice problems where I subtract x on the left and gain x on the right, and put them into the mass action expression to figure out what x is. So x squared over 0.03 minus x is equal to 1.8 times 10 to the negative fifth, so that then I can figure out how much hydrogen ion I have, so that then I can do the negative log of that to get the pH. Not fun, time consuming, but certainly not something you haven't seen before. And for these particular problems, again, you can apply the 5% rule. It's perfectly okay, especially with these k values that are so small, smaller than 1 times 10 negative fifth. So you can ignore that x in the denominator. Your math goes a little bit faster. Okay? All right, so that's how you would do part A. You would solve for x, then you do the negative log of x. That gives you pH, because that's your hydrogen ion concentration. All right, let's take a look at B. So B, our initial concentration is 0.03. You use 30 milliliters, and now for part B, they're starting to add some acid. They're starting to add 10 milliliters of acid, so my final volume is 40. Okay, so over here the concentration is 0.025 times 10 over 40. And I should have no ammonium present initially. All right, so let's see, 0.03 times 30 over 40 happens to be 0.0225. And then over here, 0.025 times 10 over 40 is 0.00625. You have no ammonium present initially. All right, so this is again a limiting reactant problem. All of these hydrogen ions are going to be consumed by the ammonia floating around. So you're going to lose 0.00625. You lose 0.00625. Get none of this. You gain that over here. Alright, so you end up with 0.00625 underneath the ammonium column, and then 0.01625 under the ammonia column. Alright, so if you look at this particular case, you have a certain amount of a weak base sitting in a beaker with a certain amount of its conjugate. And if you recall from our last lecture, when you have a mixture of a weak base with its conjugate, we call that a buffer. So if you wanted to figure out the pH of this particular buffer, you'd have to use the Henderson-Hasselbalch equation. All right? Now, do you use the pH version of the Henderson-Hasselbalch equation, or do you use the pOH? Well, in this particular case, because I'm given Kb, or I know Kb, and I know that I'm starting with a base over here, I'd use the pOH version of it. So the pOH version of the Henderson-Hasselbalch equation is that the pOH is equal to the pKb, or the negative log of the Kb, plus the log of the conjugate over, or the concentration of the conjugate over the original weak base. So the pOH is going to be equal to the negative log of 1.8 times 10 to the negative fifth plus the log of 0.00625 over 0.01625. All right? So once you put this in your calculator and you simplify that out, you simply subtract from 14 to get the pH. Next, take a look at C. In part C, they want me to add 20 milliliters of acid. Okay, so we would do basically the same thing. You adjust the concentration, so it's 30 over 50. You adjust this concentration, it's 20 over 50. All right, so let's see. So this is 0.018. And for the acid, it's 0.01. Okay, this is still limiting. So you end up, you had no ammonium present initially. You end up with no acid left, 0.008 ammonia, and 0.01 ammonium. Again, what you have in your beaker at the end of the day is a mixture of a weak base with its conjugate. So you have to go back to the Henderson-Hasselbalch equation to solve for those, because what you have is a buffer on your hands. You're in that flat part of the titration curve. Remember in the lab, this flat part of the graph in the buffering region. So you're going to do pOH is equal to pKb plus log concentration of conjugate over concentration of weak base. All right. Once you have that value, again, subtract from 14 to get the pH. All right, let's take a look at D. So for part D, they're adding 35 milliliters of acid. So we're going to adjust those concentrations for these volume changes. All right, so let's start with the concentration of hydroxide. It's going to be 0.03 times 30 over 65, or 0.0138. And then over here for the hydrogen ion, it's going to be 0.025 times 35 over 65, or 0.0135. Okay, again, got no ammonium present initially. This is still limiting because this is still less than that. You're left with 0.0003. None of that. We're going to gain 0.0135. 0.0135 is what you have present at the end. And one more time, what you have in your beaker is a mixture of a weak base sitting with its conjugate acid. You're going to use the Henderson-Hasselbalch equation one more time to figure out the pH. All right, now let's take a look at part E. Let's adjust these concentrations. So now we're going to add 36 milliliters. So we're going to end up with a volume of 66. So let's see. We have 0.0136 molar ammonia. And 0.0136 molar hydrogen ion, and no ammonium. Alright. Ooh, this is ugly. Alright. We're going to end up with no ammonia, no hydrogen ion, but we're going to have some ammonium floating around. Okay, well, does ammonium have an effect on pH? And the answer is yes, it sure does. Because ammonia is a weak base, this is its conjugate, and what we learned is that conjugates of weak bases themselves are strong acids. So if you end up with just a number, 0 under every column except for 1, and that number that you end up with is basically a value for a strong conjugate, you're going to have to do a second Rice chart. So why is this a strong acid? It has to do with the secondary reaction that occurs in that beaker. So this ammonium is going to react with some of the waters floating around it, and it is going to donate its proton back to water to make hydronium and back to ammonia. Alright, so this reaction here is best described by a Ka. Alright? This initial concentration, 0.136, comes from the ending concentration from the first Rice chart. I'm going to have no hydronium present initially, no ammonia present initially. In terms of losing ammonium, it's going to be X amount. I'm going to gain X for hydronium, gain X for ammonia. Your E line is going to read 0.0136 minus X for ammonium, X for hydronium, and X for ammonia. To calculate out X, you're going to say X squared over 0.0136 minus X is equal to the Ka. However, you don't have the Ka, but you do have the Kb. And in order to solve for this, it's really straightforward. Remember, the Ka is nothing more than Kw divided by Kb. So you're going to go through all this process basically to solve for X. Alright? So you're doing two Rice charts. The N line for the first Rice chart feeds into the I line for the second Rice chart. And then the X value is what you want, because that's the hydronium concentration sitting in that beaker after that secondary reaction is done. And once you have that, then you can simply find pH by doing the negative log of this particular value. Long and tedious, but again, nothing you haven't seen today. You're not familiar with. You're familiar with these. You've seen plenty of these before. All right, let's take a look at F. For part F, they're adding 37 milliliters of acid, so it's going to be 0.03 times 30 over 67. This is going to be 0.025 times 37 over 67, and there's no ammonium present initially. All right, so I'm smelling another one of these two rice chart type questions for this. All right, so this is 0.0134 for ammonia initially. 0.0138 for hydrogen ion initially, and 0 ammonium initially. Oh no, this is even better. Oh, I like this one. This one's easy. All right, so my limiting reactant is the ammonia, so I'm going to subtract 0.0134. I'm going to subtract 0.0134. I'm going to gain 0.0134. All right, I have no ammonia present at the end. I have 0.0004 underneath the hydrogen ion column, and then I have 0.0134 under the ammonium. All right, here's the deal. You have a number under that column, you're golden, because all you have to do is do the negative log of that value to get the pH. Don't worry about this number whatsoever. All right, so because there's no real, the Henderson-Hasselbalch equation does not, is always in terms of the weak thing and its conjugate. It's not in terms of the hydrogen ion and the conjugate. So if you have a number under the hydrogen, you're done. That's it. That's all you want is a number underneath that column. All right, that's it. Go and do the questions in the book. They're very similar to this. They're tedious. My suggestion to you is go ahead and set up the rice charts and do all those initial calculations for volumes, and then for all 5-6 parts. That's probably the longest most time-consuming thing. And then go through and do the rice charts, figure out whether you use just the pH equation, the pH equation, or Henderson-Hasselbalch. If you have any more questions, I'll talk to you on Thursday. All right, bye.